Okay, lecture 3, absolute value and exponents. Let's begin with absolute value first. An absolute value of a number is any number that you have and then you just want the actual value of it away from 0. So even negative numbers will be getting just the positive value. And if you want to think about it, any number that you have, positive or negative, will be just whatever the number it is that is positive of that, because you want the actual value of it. In math terms, the absolute value is written with solid bars that are vertical, like so. These vertical bars, absolute value of A is equal to just A, or the negative of A is just A. As long as these numbers happen to be greater than or equal to 0, or the negative value would just be less than 0. Regardless, on the number line, any value from 0, like a value of A, if you measure this, it's essentially just A. That's just the absolute value. You want to know how far away from 0 is this number, and it just happens to be A. Same thing for the negative. How far from 0 you are, that negative A is. It's just A, because there's no really absolute value of just negative A. It's just a positive value, like how far from 0 you are. If you have a tape measure and you just measure each direction, you just get the positive value of that. And that pretty much defines what your absolute value is. And I'm pretty sure that's all you need to know for that for now, until it becomes more apparent later on in the series. Alright, that's about done with that. Exponents. The meat of the topic for today. Exponents are a way to make multiplication easier, especially if you're multiplying the same number so and so amount of times. The general form of an exponent would be two parts. You have the base itself, like the number where you multiply, and an exponent, n, where n represents how many times you want to multiply the number a. As an example, you write this out as a times a times a up to a, where this collection is n times. The basic example will be 2 cubed. It's equal to 2 times 2 times 2, where your base is 2 consistently, but your n is 3, because you want to multiply 2 3 consecutive times. 2 times 2 times 2, or the power. This a is called the base. This n is called the power. And this is the most basic definition of what an exponent should be in the most introductory of sense. The next part you should know is what happens if you have a negative exponent, power, or a 0 power. Let's start with the 0 power. If you have any exponent with the power of 0, it basically means you want to multiply this 0 times, which will be just 1. It will just default to 1. Anything raised to the 0 power, even like 1000 to the 0 power, is just 1. But when you think about infinity raised to the 0 power, that's where you exit pre-calculus territory and begin entering into calculus territory, so definitely it'll be a whole nother subject. For the time being, you just need to be worried about any number raised to the 0 power that is not infinity or negative infinity and gives you 1. For the negative exponent, any number with a negative exponent just means you want the inverse of it. So a negative n exponent. It basically would be written out as 1 over a to the nth power. as in the inverse of it. If you know these tricks, it will definitely help you out when you start simplifying these values in the problems that will be coming up. Once you get this out of the way, now we need to know the general laws of the exponents, just like in the very first video where we need to know the laws of commutative, distributive, associative property, and so on, especially negative numbers and fractions. You have laws of exponents. And lucky for you, there's 5 laws. Not too bad. Start with the first one. A to the m power multiplied by a to the n. So if you multiply 2 exponents together with the same base, it basically would equal to the same base power, but the exponents are added together. An example of that being 2 to the third times 2 to the second. It'll give you 2 to the fifth. If you want to break it out, it's 2 times 2 times 2. This is 2 to the third multiplied by 2 times 2, which is 2 to the second. And this is equal to 2 to the fifth. Because there's now 5 sets of 2, or 5 times 2. Well, it's not 5 times 2. Well, you take the 2, but you multiply it 5 separate times. Only 2. And it'll give you, if I remember correctly, this is what, 8 times 4, 32? Yep. The next law would be division. When you have common bases, a to the m over an is equal to am minus n. Using the same example, 2 to the third, 2 squared is equal to 2, 3 minus 2, which is equal to 2 to the first, which is 2. If you want to write it out, 2 times 2 times 2 divided by 2 times 2 is equal to, see these 2's cancel out, just 2. The third law would be if you raise your exponent to another power. A to the m raised by a power of n is equal to a m times n, multiplicative of exponents. Again, 2 to the third raised to the second power equals to 2 to the sixth. If you want to write out the numbers, 2 times 2 times 2. If you square that, you get another 2 times 2 times 2. You get 6 of them, which will give you back 2 to the 6th. The fourth law, let's see. If you have what? 2 bases. If you have 2 numbers, a, b, raised to the power of n, it will be the product of a to the n and b to the n. The example here will be 3 times 4 squared is equal to 3 squared times 4 squared. It's either you do 4 times 3 and then you square, or you do 3 squared times 4 squared. In this case, it'll be 12 squared will be 144, or here it'll be 9 times 16. Do a quick math. 9 by 16, 54, 144. And the last law, I'm going to make some room here, would be division of 2 bases. The fifth law will be a over b raised to the power of n is equal to a over n over b to the n. Your example of that will be 3 over 4 squared is equal to 3 squared over 4 squared, which will be 9 over 16. Alright, so that pretty much concludes all the law of exponents for now. Before going into the opposite of raising exponents, we have radicals, or root components. Anyways, notice how when you do these laws, you have common bases, and then you can combine exponents easily if you have common bases. For uncommon bases like the last two laws, 4 and 5, just make sure that they are both grouped together by the same exponent, and then you can do some of those laws there as well, which is what we just demonstrated for 4 and 5 specifically, and follow exactly in that type of format, and you should be good. I think there's 2 more laws to go to. Yeah, there's 2 more laws here. The 6th law. Sorry, I lied to you. It's not really 5 laws, it's 7. A over b raised to the negative n is equal to b over a raised to the n power. So this applies now with the negative exponent, because you take advantage of the fact that when negative exponent would mean an inverse power. So if you have an inverse or inverse, you just basically just do the reciprocal and you maintain the power that is positive. An example would be 3 over 4 again. 3 over 4 to the negative 2 power is equal to 4/3 raised to the 2nd power. Or if you want to apply the 5th law again, 4 squared, 3 squared. Get right here, 4 squared, 3 squared. 3 squared, you get 16 over 9. And the last law will be, if you don't have them grouped together with the same power, let's say you have a to the negative m power. I'm always messing up here. A to the negative m power, my bad, and b to the negative n power. Well, now you have different exponents, except you can apply the same idea. B to the negative n, a to the minus n. You could just say b to the n over a to the m. Because you know that any exponent with a negative happens to be just its inverse with the positive. And if you have 2 numbers that are like that, a to the negative m and b to the negative n, you can essentially write 1 over a m divided by 1 over bn. So if you remember from the first video, keep, change, flip, keep the first exponent, multiply the fractions of the reciprocal of the other, bn over 1, which will give you bn over am. And henceforth to give you back here. Using the numbers again, 3 over 4, 3 to the negative 2 over 4 to the negative 2 is equal to 4 squared over 3 squared, which will be 16 over 9. And this pretty much concludes just the exponent part. Now we're going to go over something else called radicals. With radicals, similar to exponents, you take a number and you divide it by another number a certain number of times. And it is essentially the same number you take to divide it with. Where exponents, on the other hand, you take a number and then you multiply it by itself a certain number of times, which is called raising a power. For radicals, it's taking a root, or taking some nth root. The most common forms of whatever you want to call the radical is the square roots, where it's just the radicand, or the radical symbol, and the a, or some number a that happens to be inside of it. And usually it is equal to some value b, where b squared is equal to whatever's inside the radical, a. And also b has to be greater than or equal to 0, because you cannot have the square root of a negative number, because there's no such thing. And impossible to do so because you know if you take a negative number and you square it, you get a positive. So the more general definition of it, of a radical, is you have the same radical symbol with the some number a equal to b, except for over here, this little lip, you have n, where n is a rational number. And it's equal to b raised to the power of n is equal to whatever is inside the radical a. If you want to be technical, a radical would imply a square root, while a root will imply any root depending on whatever number that you put in front of the word root. So if you want to take the third root or cube root, you're assuming you're taking the third root of some number, or the fourth root, fifth root, so on and so forth. Similar to exponents, radicals also have properties to work with that will be easier to manage when you begin to work with them and you simplify them in later chapters. So you have a series of rules here, very similar to exponents, that you can work with, where you combine, you break them up, and here we go. With the first one, you have the nth root of the product inside the radical is equal to the nth root of a multiplied by the nth root of b. The second one is you have the nth root of whatever division or quotient in the inside, a over b, is equal to the nth root of a divided by the nth root of b. The third one, you raising a root of m to another root of n of a is equal to the product of the roots, m times n with an a inside. And I believe the last two is you have an odd exponent, n a is equal to a if n is odd. And the last one is the even exponent, absolute value of a, if n is even. Putting the numbers into perspective here, with the first example, let's just take the cube root of -8 multiplied by 27. And this is equivalent to taking the cube root of -8 multiplied by the cube root of 27. And if you simplify these, you know that -8 cube root is just 2 multiplied by, well, -2, excuse me. If I can get -2 multiplied by the cube root of 27, which is just 3, the result is -6. For the second one, you can do the example of a quad root of the quotient 16 over 81, which is the equivalent of the quad root of the numerator divided by the quad root of the denominator, and it's equal to 2 over 3. Third one, let's just take the square root of a cube root of 729, and it's equal to the sixth root of 729, which is equivalent of 3. The fourth is taking the cube root of a negative 5 to the third power. So let's do here n. Forgot to add that part. A to the n equals a. Here we go. So let's take the cube root of negative 5 to the third power. And it's equal to negative 5. Because you're taking the third power and you're undoing the third power with the cube root, and you're just getting back negative 5. Now, the flip side of this, a second example you can do here is taking, let's say, the cube root of negative 27. That should equal to negative 3. Because negative 3 times negative 3 times negative 3 is negative 27. And the fifth one, let's just take what you call square root of 4. It's essentially equal to just 2 plus minus. The plus minus in front means you can have two answers. 2 squared will give you 4 again back on the inside, or negative 2 and then you square it will give you 4 again. Knowing this is very important when you solve equations in later on in this course, because sometimes when you take a square root of a number, you end up having a positive root and also a negative root, because both of them will also give you the solution to get back the original number you solved for. Now, knowing these properties, the next session deals with rational exponents, combining what you know for, let's say, exponents and radicals into more simple and compact understanding, instead of having all this fly in your head and just take up so much memory. The general form of an exponent here, rational exponents, would be, let's say, a to the 1 over n power is equal to the nth root of a. The general form of rational exponents is equal to a raised to the m over n power, where m is the power or exponent, n is equal to the root or the radical. A m to the n is equal to a to the m with the root of m, like that. So far so good. And also there's a catch that if n, the root, is even, a must be greater than or equal to 0, because you cannot take the square root or an even root of a negative number, because you won't be able to get that number back. With odd roots, you can have positive or negative and you can get back the original number, no problem. And the last thing we want to go over for today would be something called rationalization, or rationalizing the denominator. When you begin to simplify expressions and equations, it becomes very, very hard to mess around with radicals or square roots when you begin to start seeing them in the denominator. Minator. Got it. Okay. So this technique exploits the use of multiplying the identity of the number that is in question by 1, because you know anything times 1 is itself. So it's not always necessarily have to be just the number 1. The number 1 can be a ratio of two numbers that divides itself and it'll give you back 1. For example, let's say you have a number of 3 over square root of 5. And you want to simplify this because you want to bring the radical on the top or the root on the top because it doesn't look right for whatever reason. This is equivalent to taking itself and multiplying by 1, where you'll get the same answer again. Instead of 1, how about you multiply by the top and bottom, numerator and denominator, by square root of 5. Because knowing if you multiply two numbers of the same base, you can combine them together with their exponents. So since you know that the square root would be a half power, you're adding two half powers and you get the power of 1, which is just the number inside. And this is equivalent to 3 square root 5 over 5. And the side note would be square root of 5 is multiplied by square root of 5 is equal to 5 1/2 power times 5 to the 1/2 power is equal to 5 1/2 plus 1/2, which is 5 to the first 5. Gets you back here. Knowing this is very vital and important when you begin to do something called conjugates, or solving equations, or completing the square. For solving complex well, it's not complex equations, more like parabolic or quadratic equations later on. And that's pretty much it for now.